morning all. Good morning all. Okay. Where's my thing? Hope you are having a good start today. Today we are going to discuss unit number 6. But before doing that, yesterday I posted your grades. Were you able to check your grades? Some of you need to do a few things. I sent emails to those of you that need to do something today, or just commented on the Blackboard gradebook. Okay, so please, if you haven't checked your grade, do that. Make sure that you understand everything, and if you have questions, today is a good day for make questions regarding your test. All right. Okay. Any question before we start? Okay, Dylan, I think yes, you are here. Dylan, this is the question that you asked yesterday. Is it okay if I discuss this question with everyone? Right. All right. So we're going to start with this one because it's a good refresher of what we did on last class. This is for unit number 5, and the goal here is to identify properties of the function that we are seeing here. Okay, this is not the color that I like. Okay, so here there is our function. I'm going to write it in the notebook just in a moment. And we need to go through its properties. All right. Once we gather all those properties here, we are going to do the graph following these steps. Plot the points, identify the behavior, and then finishing the graph. Okay. So here is our polynomial function. Quick question, is this the standard form or the factor form? It is the factor form. Okay, every time we see this, that we have a polynomial with that there's no separation of the terms, there's no addition or subtraction, that separate terms. Yes, there is addition and subtraction within the parentheses, but outside the parentheses, what we are seeing is multiplication. That means that we have the factor form, and each of these 3 are factors of this polynomial. The 3 are linear factor because the degree of each polynomial inside those parentheses is 1. All right. So we are going to start identifying the degree and the leading coefficient. How can we identify the degree of a polynomial if we have the factor form? From the factor form of a polynomial, how can we identify the degree of that polynomial? Who can remember that? Amanda, I like that you are referring to the exponents. Yes, there is, you are close, but not quite there. The exponents here are important. But what exponent? Okay, for the dynamic leading term with the exponent and the exponent of the leading terms. All right. I like that you are using the phrase leading term. So each of these linear factors, what we have within the parentheses, they are polynomials, right? Hence, we can identify the leading term of each of those polynomials. The leading term of each of these polynomials, they are linear. The x variable contains an exponent of 1. Okay? So we need to take into consideration the degree of those factors and the exponent that is on top of the factors, on the closing parentheses. All right? So we use those. So for on the first one, we got 1 times 1. From the second one, we got 1 times 2. And for the third one, we have 1 times 2 again. We add those, and the value is 5. Hence, degree of this polynomial is 5. Right? So basically, we got the degree of the factor times the multiplicity of the linear factor. We could say that. I think that's the proper way to identify both factors here. The degree of the linear factor, which is 1, in this case is a linear factor. So the degree of the polynomial that is within the parentheses times the exponent that apply to that entire set of parentheses, right? That's the multiplicity of the linear factor. So we do that, we add all those multiplications, or all those products, and we got the degree. Any question on how we do that? Right? If there's no question, then what is the leading coefficient here? What is the value of the leading coefficient? It's positive 1, right? How do we know that? When we have the factor form, this space here is the space where usually you are going to find the leading coefficient. If the leading coefficient is 1, we don't write it, all right? But that way you can identify that. If there's nothing here in this space, in the factor form, then it means that the leading coefficient is 1. And from this information, what can we get from this information? From the sign of the leading coefficient and the degree. Why we need to know this? Oh, what can we get? The end behavior, yes? The end behavior. So we have that 5 is odd, and we have that the leading coefficient is positive. That's all what we need. So we know that the shape of its graph is going to be something like this, but in the middle is not necessarily going to be this, but we can get from that shape the end behavior. So we have the end behavior of the graph, right? The shape is similar to a cube function shape, or cube function graph shape, but we do not exactly what's happening on the middle because the degree is 5. But we are for sure, we know the end behavior, the end behavior of the graph. Okay. All right. So that's A. Then for B, so here I believe in Alex you have like a multiple choice or a menu, you need to select the one that says falls to the left and rises to the right, something like that. Okay, so on B we are going to list Dylan. If the degree is even, you will have a parabola shape. So if our degree is even, then the behavior is going to be like a parabola shape, although we don't know what's happening in the middle, but on the ends of the graph we know that it will go both sides to go up if the leading coefficient is positive, and negative if the leading coefficient is negative, then the ends will go down. Okay, so again, if the degree is even, we will have a parabola shape, so it means that both ends go to the same direction. Positive go up, negative goes down. Okay, so now I put the word here zeros, but from B we are going to get more than the zeros. We are going to get the zeros and the behavior and the x-intercept and so on. So for that we are going to do this following table. This table is going to help you to complete all those categories or to find all those properties. So let's start with the linear factors. From the linear factor we can get the zeros. Then we can get the x-intercepts. Then we are going to get the multiplicity of those zeros, and lastly we are going to get the behavior. Behavior. Okay, this word is always behavior. All right. Okay, so from the linear factors we have x plus 2. I should copy and paste this. Let me see what I get here. Okay. Okay, I'm gonna leave the exponent of the factors because we are going to use them to identify the multiplicity of them, of the factors or the zeros. All right, so those are the three factors that we have: x plus 2, x minus 1, and x plus 1. Yes, and we are seeing their factors, their exponents or their multiplicity. All right, so the zeros. Linear factor. The structure of a linear factor is that it is x minus r, r being the zero of the polynomial, or the root of the polynomial. Hence, we got a zero of x equal r, right? So the opposite value of minus r, because if we add r times, add r minus r is going to be zero. So that's why we got the zeros. So you are going to focus on the constant term. The constant term is positive. Well, the zero is its opposite value. It's negative 2. The constant term is negative 1. So we have a zero of positive 1, and then vice versa. Positive 1, negative 1. From the zero, we can get the x-intercepts we can get the x-intercepts because we know that all the y values are going to be 0 because we are working with x-intercepts. Okay? So we just take this value, which is -2, +1, -2. Okay. So multiplicity, you are going to identify the exponent on those factors. So we have multiplicity here. Is 1, so odd. 2 is here is even and even. And with the multiplicity, we can get the behavior of the graph on those x-intercepts. Okay. Remember that in the x-intercepts, the graph is going to touch or it's going to intersect with the x-axis. Now we need to determine if the graph is going to cross the x-axis or it's just going to bounce at the x-axis or touch the x-axis. When it is odd, it means that the behavior crosses, and when it's even, it touch or bounce. Okay. The way you answer in Alex is by listing the zeros that crosses the graph. So that's 1, the one that with the odd multiplicity, and the zero where the graph touches, but that does not cross the x-axis. That means 0 with multiplicity that's even. All right. So C is going to be the y-intercept, and the y-intercept is going to be very easy because what we need to do is to plug in 0 into x. And solve for the function or the polynomial. This is going to give us +2, hence y-intercept is 0,2. And with this information, we are ready now to graph the polynomial function. Okay. All right. So next thing that you will do is first plot the points. The point that we have are the x-intercepts and the y-intercept. So they're going to be around here. So here's our first x-intercept, then -1 is here. So second x-intercept, 1 around here. That is our third x-intercept. And then we have the y-intercept, which is around here. So those are the intercepts. Now, from A, we got the behavior. We know that from the left, it falls. So we can start from this point, going down, it falls. And from this point here, it rises. Okay, so that's the behavior. I know that the graph will cross to, or we at least will cross or touch on this x-intercept, all right? So that is why I connecting the end behavior with those 2 points that are on the both extremes. Okay, so on the left one it falls, from the left one it falls, from the right side it rises. Now, from the behavior of the x-intercepts, we know that a negative 2 it will cross we know that at positive 1 it will touch. So if the graph is above the x-axis, it will stay above the x-axis. So we will have something like this here. At negative 1 it touches again, because on the left side I have the graph above the x-axis. I know that it will do something like this here. Okay. Then we need to connect this. And I know that the graph needs to pass through here because I have this one. I have a y-intercept. So I am connecting this part here. I am not really sure if these portions are correct. This is just a representation of what the graph for this polynomial is, okay? But at least with the properties that we gather from these items, we are for sure uncertain that the x-intercept are here, that is the y-intercept, that this is the behavior, and this is a representation of the shape of the graph, or the graph of this polynomial, right? And there you have it. One thing that you can do, if you want to make sure that everything here is correct, let's go to Desmos. Desmos is a free graphing calculator website. What was it? X plus 2. X minus 1 squared, and then x plus 1. Okay. So that is the graph. Okay. So that's the graph. So my representation is correct. Okay. Let me put a print screen here. By okay. So now we can compare the actual graph and the representation that I did. Don't judge me by my drawing abilities, but we can see the end behavior going false to the left, rises to the right. We can compare the x-intercepts. We have 3 x-intercepts, the behavior of the x-intercepts. Another thing that is important here is that you can see that we have 4 turning points. So 4 turning point means that at least the degree is going to be 5, and that's correct. Or the degree is 5, at most we are going to have 4 turning points. Okay. Any question on this one? What you are seeing here, this is a complete written work that I wanted to see on your assessments. Okay, if you have this exercise, what you are seeing here, this is the written work that I will expect to see from you, from your exercises. Any questions? Okay. Okay, Halima, we could do a few things. We could see the graph, and we can see all these turning points. Okay, so we can count this turning point. 1, 2, 3, 4. That's from the graph. Okay. Now, if we know the degree is 5, if the degree is 5, then at most 5 minus 1, 5 minus 1, which is 4 turning points. Okay. This is a relation between the degree and the number of turning points that you need to know. The degree is 5, at most 4 turning points. If we have 4 turning points at least, the degree is going to be 5. Okay. Any other questions? The only, Rachel, at this moment we are not going to know that. I just assuming that around the y-intercept there should be the turning point, but not exactly, as we can see here, the y-intercept is not the turning point. Alex is going to complete the graph for you, and if we want to know exactly where the turning points are, then we will need to do the derivative of the polynomial. But that's for a topic for calculus, a calculus class. Okay. So we are just scratching the surface of the polynomials. Later on other classes, you're going to see what else can we do with these properties and how further we can advance with other mathematical techniques. Okay. When you are taking calculus, you are going to learn about derivatives and derivatives. With the derivatives, you can identify exactly where the turning points are. Okay. Any other questions? All right. So unit number 6, you're working on Dylan, is now about the zeros of the polynomials. Okay. So now our goal here is going to be able to identify the zeros of any polynomial. Here we need to go over things that we need to know before unit number 6, and we'll need to learn a few techniques in order to achieve our goal here. Okay. All right. Things to know before. Okay. And this is going to be things to know before. Yeah, that's correct. This is going to be like a review of what we have done. So you need to know the difference between the standard and factor form. Okay, you need to be able to identify the standard and from the factor form of any polynomial. All right. You need to remember that a factor is like a building block of a mathematical expression, math expression. Okay. Use as a building block of a mathematical expression where we put together those building blocks by multiplication. For example, the number that we saw on the last class, 21. So the building blocks of 21 are 3 and 7. We multiply them together and we got 21. If we are going to talk about a polynomial, our subject on the last class was 8x plus 3, 7 x squared minus 8x minus 7, okay, and this is all equal to 8x minus plus 7x plus 7/8, and then x squared minus 1. Okay, so basically we call a factor any of these that we use in a multiplication to construct the mathematical expression. Okay, could be whether it is a number or a polynomial. From the building block or the factors, there's an important property. And that property is that if we divide, when we divide by a factor, right? If we have a mathematical expression and we divide it by one of its factors, divide by one, I should put here by one of the factors, divide by one of the factors. The remainder is that how you spell remainder? Remainder, yes. The remainder is 0. This whole unit will be based on this important property. When we divide a mathematical expression by one of the factors, its remainder is going to be 0. We can see that from here. When we divide 21 by 7, for example, we know the quotient, the result, is going to be 3, right? If we do long division of this, we have 3 here. So 3 times 7 is 21. We subtract and we got 0. Remainder. It is here. It is 0. The remainder is going to be 0 because we divide 21 by one of its factor, 7. We can see that if we can apply this same property for polynomials. Yet for polynomial it's going to be a bit more complicated because we are not used to divide polynomials. All right. So right now I do not know exactly what the quotient is, the result of this division is, but I know because x plus 7/8 is a factor of the polynomial that we have on the numerator, the remainder is going to be equal 0. Okay? Regardless what the quotient is, I know that the remainder is going to be equal 0. The polynomial that we have on the numerator is in its standard form. But let's see how can we do this division without going through long division or things that are might complicated or tedious. So if instead of using the standard form of our polynomial, let's use its factor form. Where are you? Okay. No, that's not what I want. Okay, there you are. So let's see how easy now is to do the division of these two polynomials now that the numerator is in its factor form. What should I do here? How can we now divide or do this division? What do you think we need to do in order to get the quotient? Help me undo this division, or tell me your idea of what should I do. What do you think?
Doesn't the x, actually no, never mind. I just noticed that it was the same.
I think you are right.
I was gonna say that those two cancel out.
Mm-hmm. The one that are in pink. Mm-hmm. We have a common factor between the numerator and the denominator, so we cancel them out. And then we are able to get the quotient. Okay, so here you are seeing one of the uses of the factor form. We need to divide a polynomial, try to get its factor form, because then using just multiplication and division is easier to do division, right? But the important thing here is that the remainder, it is 0. Okay, so those are two things that we need to know before. There are more, so let me create another page. You need to remember that the zeros of a polynomial are related to the linear factors. Of the polynomial. Okay, so if r is a 0, then we have a linear factor of x minus r. In the example, -7/8 is a 0, hence x plus 7/8 is a linear factor of the polynomial, okay? The polynomial that we are working with. So, number 4, it is important because now we need to be able to identify the set of numbers that we are working on. Okay, and let me stop here for a moment, because in our class we haven't go over this. Okay, you might have seen this before on your classes. Okay, but I just want to emphasize on this because this is crucial to this unit, because we are going to identify zeros, and those zeros could be real numbers, irrational or rational numbers, or it could be imaginary numbers. So let's first split these two sets into the two main sets that we are working on: real numbers and imaginary numbers. Okay, so these are the two main sets that we are going to be working on. Imaginary number, real numbers split into two subgroups: rationals. Okay, rational numbers. These rational numbers are numbers that you can put in a fraction form. Example, 1 over 2, right? That's a fraction. That's a rational number. The decimal representation is 0.5. Okay? See that we have the decimal representation of this value. It ends, or you are going to find a pattern in the decimal representation. For another example, 3, 1 over 3, that's 1/3. So we know that the decimal never ends. Okay, so we're going to have 3, 3, 3, 3, 3, 3. But because there is a repeating pattern, okay, that way, that's one way to identify that 0.3 or 0.3333 or 1/3 is a rational number. So the most, or the easiest way to identify a rational number if we are able to put that number or that value into a fraction, hence is a fraction, is a rational number. Integers are also rational numbers. Okay, any rational number can be, any integer can be written as a fraction. Okay. So those are rational numbers. Irrational number, on the other hand, are going to be numbers, real numbers, but real numbers that we are not going to be able to put those values into a fraction. What are those values? A very common example of irrational numbers. The value of pi, 3.4, and so on. There is no common pattern, there is no repeating pattern in the decimal representation of that value, and there is no way to put that value into a fraction. Hence, we use the notation for pi, an important number. There's other number, e. I believe this is 2.7, something like that. I don't know. Let me see. Where are your calculator? Do we have e here? Yes. E, 2.71a, and so on. Okay, that's another irrational number. Another one, square root of 2, natural log of 2. Okay, all these four are example of irrational numbers. Okay, numbers that we cannot put into fractions. On the other hand, we have imaginary numbers, and then only the name can throw you off, right? Imaginary numbers. Well, maybe we are doing now some kind of magic here in math. No, that's not the case. Imaginary numbers are the history behind the name of this group of numbers is because for so long they were present, but since, well, maybe I think I'm making things complicated, but the thing is that if we just working in a coordinate plane with real numbers, we are not going to be able to see the imaginary numbers, hence the name of imaginary numbers. But I don't want you to feel scared about just the name, okay? If you know how to, if you know the properties of the imaginary numbers, you are going to see that you are going to treat them as any other value, okay? Imaginary numbers are based off the square root of -1. The square root of -1, and whenever we have this, we are going to use the letter I to represent the value of square root of -1. Yes, in your calculator you are not going to see this because your calculator is based on just on real numbers, okay? But imaginary numbers are numbers that we use in math, okay? And they have a lot of application. I'm not an expert on the situation where imaginary numbers are used, but engineering, especially when you're working with fluids, I believe there's a lot of use of imaginary numbers. Okay, but like I said, I'm not an expert on the area, so I'm not going to go deeper on that. In the mathematical aspects, we just treat them as just any other value. Okay, and we use their properties, and we use the operation the way, and the set of rules that apply to them the way they are applied to them. Another example is it could be square root of -9. Whenever we have this, we can separate this into a multiplication of square root of -1 times square root of 9. Solving square root of 9, we got 3. And then -1, square root of -1 is I, so we got 3i. Okay? And that would be the imaginary number. See, that's the way that you are going to work with imaginary numbers in this class. Any question on this? All right. So that's 4 and 3. Number 5. What page is this? Number 4. When you need to know when and how to use the quadratic formula. Okay, so when are we going to use the quadratic formula? Can you tell me on the chat why would you use the quadratic formula? In which scenarios would you use the quadratic formula? When you might use the quadratic formula? In what type of exercise? Do you remember? Okay. The quadratic formula, you are going to use it whenever you have the standard form of a quadratic equation and you need to solve that equation for 0. That means what is the value of x that makes the standard form of the quadratic equation equal to 0. So you need to have the standard form of the quadratic equation, and that equation need to be equal to 0. So that is the scenario where you are going to use the quadratic formula. Then you use the quadratic formula to get the value of x. All right? Now, what is the meaning of this plus and minus? Well, we are working with a quadratic formula. We will have a parabola There, oh, no. Oh. Okay, let's do this again. There you have it, that's my parabola. Okay, so a quadratic formula, and the graph of a quadratic formula is a parabola. Whenever we are looking for for the quadratic equation equal to 0, right? For these x values, we're looking for the x-intercept, or hence the zeros of the polynomial. Because we have a parabola shape, right? See what are the options for the x-intercept, or how many what are the options for the number of x-intercepts that we could have. We could have 2 x-intercepts, plus and minus. Okay, we could have 1 x-intercept, or we can have non-x-intercepts. Okay, you can determine without looking the graph by the quadratic formula. You can know how many x-intercepts you are going to have, or real x-intercepts. And you are going to know that based on the determinant here. What is inside that radical, that square root, b squared minus ac, is going to tell you how many x-intercepts you are going to have. So that's why we call this the discriminant. When this b squared minus 4ac is positive, when it is positive, you will have 2 x-intercepts, the plus and minus, the value when you add, the value when you subtract. When this is equal, the discriminant is equal to 0, you cancel that plus and minus, hence you are going to have just 1 x-intercept. Because the coordinate plane is based on 2 number lines, and those number lines are based on real numbers. When the discriminant is negative, you will have no x-intercepts. The value that you are going to get as a solution for this quadratic equation is going to be 2 imaginary numbers. Hence, the parabola you will not see in the coordinate plane based on real numbers only. You are not going to see an x-intercepts. Okay? In order to see those x-intercepts, you need to change the x-axis with the x-axis that represent the imaginary numbers. Okay, but we are not going to do that here. We are going to continue working with our coordinate plane and the real numbers. Okay, the only thing that you need to be able is to identify if the solution of this quadratic equation is going to be real numbers or imaginary numbers, or a combination of both. Okay, so from these two, we are going to get real numbers. And from this one, we are going to get an imaginary numbers. Okay? Real number, remember, it could be a rational number or an irrational number. Okay? Any questions so far? Okay, so like I told you, units 5 to 6, maybe 5 to 8 are the most heavy units. So you are going to see this on these units. But once you finish with this one and you understand them, everything is going to be easier. Okay, we have 14 units. So this is the middle part, and these are the more critical units. So just bear with me. All this information that you are getting here is important, and you will use this on your later math classes. and more importantly, you are going to use them on application to real life. All right. These units have a lot of uses in real life. The tricky part is how and when to apply them. All right. Another thing that you need to know is synthetic division. Okay, so synthetic division is a simplification of long division. But it's long division but simplified. Let me put that here. Okay. So I have here all the concept of how to do long division or synthetic division, because I want to focus on the example that I have from Alex. I'm just going to put this here. But if you have questions about how to do long division or synthetic division, I'm going to do synthetic division in the exercise that I have from Alex, and maybe I'm going to explain the method of doing synthetic division. But if you need help with this, let me know to separate time after the class and to go through some examples, okay, on how to do long division or synthetic division. Okay. So this is going to be crucial. That you know how to do synthetic division is going to be crucial for our exercises, because we are going to use synthetic division to get more information. Okay. But like I said, I'm not going to go to explain it here. I'm just going to put it here and tell you need to know how to do synthetic division. If you have questions, let me know to go over your questions. I'm going to do synthetic division in the exercises. I'm going to show you how you are going to use synthetic division in Unit 6 exercises, and I'm going to show you a method to do synthetic division. Okay, so those are the 6 things that you need to know before unit number 6. Okay, now we are going to do the examples, and I'm going to start with a few examples from the workshop of the day so I can help you there, and then we are going to jump to our Alex examples. Let me see. Okay, in the examples we are going to discuss the most important method for today is going to be how to use the rational zeros theorem, okay, and the strategy to identify all the zeros of any polynomial. Okay. That is our goal for today. So again, we have been here 1 hour. I'm going to stop here for a few minutes, 5 to 10 minutes. Let's take a break, and then when we come back here, we will do exercises, and you will continue seeing how we are going to use what I just showed to you in unit number 6 exercises. Okay. Any question before we go to the break? All right. Is there no question? So let's take our break, 5 to 10 minutes. Yeah, and then we're going to discuss exercise.